Hello, I'm Mr. Bob, and welcome to my Geometry Review video series. This video covers Chapter 12, Section 7, titled Dilations. By the end of this video, you will have reviewed recent lessons on locating dilation images, finding scale factors, using scalar multiplication, and finally, you will review a real-world problem. If you'd like me to cover any of these topics in greater detail, please leave your request in the comment section below. Please subscribe to this channel if you find this video to be helpful. Thank you. Okay, so now as we're getting started, I have some definitions that I'd like to go over. Dilation. In general, a dilation with center C and scale factor n is a transformation in size, whether it's getting larger or smaller. It's a transformation in size. A dilation, an enlargement is a dilation, is an enlargement if the scale factor is greater than 1. Reduction. A dilation is a reduction if the scale factor is greater than 0 but less than 1. Obviously, if it's equal to 1, it's nothing. It doesn't change at all. It doesn't get larger or smaller. If it's 0, it doesn't exist. Everything disappears. So if it's less than 1, you're taking a fraction of the size, a half of it, a quarter, or whatever. If it's greater than 1, you're 2 times, 3 times, 4 times, whatever. Scalar multiplications. Multiplying a matrix by a scalar, that's a constant value, is called scalar multiplication. And we'll see that done in this video. Okay, objective 1A, locating dilation images. A dilation is a transformation whose image and pre-image are similar. Thus, a dilation may be referred to as a similarity transformation. It is not an isometry. Every dilation has a center and a scale factor n, where n is greater than 0. Of course, it has to be greater than 0, because if not, it would disappear, right? Everything would be multiplied by 0. The scale factor describes the size from the original figure to the image, whether it's gotten larger or smaller. In general, a dilation with a center C and a scale factor n is a transformation for which the following is true. First, excuse me, the image of C is itself, that is, C prime equals C. We see that right here at the beginning of this picture, right down here at the bottom. So as this ray, which is right here, this ray, which is CR, we'll go over R, right? CR. That's the ray, CR. Well, when we change it through this dilation, the C never moves. The C is the same because it's growing and shrinking from this point. So C is itself. The pre-image is the image. Okay, that's kind of what they're showing here. This doesn't move. And then for any point R, here's a point R, here's a point R, and points all up and down this ray, R point R's. R prime is on the ray CR. So as you see, this R is on the ray, right? This R prime is on the ray. That's everything is in line. Nothing moves out of that line, okay? And then it says, and CR prime is equal to N times CR. Well, CR is this little piece right here, right? CR, and here's N. And we're saying here that N times CR, this length here, times N, is what the length of CR prime is going to be. Well, and if you look at it, you see from here to here, okay, that's about that far. This is a change of about 3. So here's 1, 2, 3, a little long. It should have been a little longer, maybe into there. Okay, so you see that this is a enlargement of 3. So we started with our point here and we moved it out to here. The CR is now 3 times larger. Okay, and objective 1B, it's the next slide in this set of objective slides, locating the dilation image. The dilation is an enlargement if the scale factor is greater than 1. A dilation is a reduction if the scale factor is between 0 and 1. So you know why it can't be 0, and why can it not be 1 is because if it was 1, nothing changed, right? The pre-image and the image would be exactly the same. So that's why we're speaking of it in these terms. And in these pictures, you can see that an enlargement says that here is C that the center is A. So here's right here, the center of our enlargement. And it says the scale factor is 2. And you can see it's 2. Look, we went from A, B to A prime, B prime. We doubled the length. How about the same thing with D to D prime? Everything's doubled. Even here, you can see that from here to here is about half from here to here. Okay, so everything's gotten larger. Everything from this point. So if you said A to B times 2, well, A prime to B prime would be twice as long on the same line. That's the importance of the last slide. Everything is in line with where you are. Okay, and here's a reduction. Center C, right, and scale factor 1/4. So here's C, the center. They put it right in the middle, right in the middle of this plane. Okay, E, F, G, H. And the scale factor is 1/4. Well, so what you've done is they've taken everything from here, like for instance, from here to C or C to F, and they moved it down from C to F prime. And if you go along this line here, you're going to find out it's 4 times smaller. Because I could probably put a lot here and probably put a dot there, and it's 4 times smaller. Or you could look at it this way. If you cut this into 4 pieces, this piece here is probably the same size. Yeah, best I can draw anyways. So you get the picture. Everything shrinks in toward that center point. There's a line that runs from the center point to the point you're shrinking or enlarging. And along that line is where the change happens. Okay, in our example 1 here, we're going to find the scale factor. So how do you find the scale factor? Well, if you can put in, you can see, we're going to show you here. The blue triangle is a dilation image of the red triangle. So we started with the red triangle right here. I'll do it in red actually. Here, red. They started with the red triangle right here, red triangle. Right? And then we moved to the blue triangle. I'm not going to draw the whole thing, but you see we moved, oh, right here, come on, blue. Where are you, blue? There you are. Um, Along the blue triangle. I'm just going to draw the corners of it. So this is a dilation that is enlarged, right? So we went from the red to the blue, it's larger. How much larger? Well, we measured the distance. So we have the distance right here of x to t is 4. Okay. So the distance from t to t prime is 8, but really this could have been 12 out here, right? Could have been, if we'd measured the entire length, it would have been 12. So what do you have here though? So you have x prime, t prime, x prime, t prime, way out here, over xt, over, so you're taking the proportion, right? So we're taking this full length from here to here, which we said is 12, and you're dividing it by the length from x prime or x to t. So that's the formula here. 4 plus 8 is 12, divided by 4, divided by where you started. Okay. Otherwise, it would have been different. It would have been different if we were shrinking it. This is enlarging it. I mean, you still have done the same equation, but the numbers would have been a little different. This would have been reducing. In other words, the denominator would have been small, would have been larger than the numerator. Well, in this case, if you take 4 plus 8 is 12 divided by 4 is 3. So this enlargement is 3. And you can see that because let's draw this up from here to here is 1, here to here is 2, and here to there, from here to here is the third one, right? So you can see the divisions. The dilation has a center at x and a scale factor of 3. It's safe to also to mention your center can be anywhere you want it to be. Your center could be somewhere out in space. And then you're going to shrink that or enlarge it from that point. It's either going to move away from that point or come closer to that point, get bigger, get smaller, whatever. Okay, example 1, check your understanding. It says here the blue quadrilateral is a dilation of the red quadrilateral. Describe the dilation. Well, why don't you take a moment and stop the video and think about this for a while and see what you come back with. I'll wait for you. Okay, I'm going to assume that you've stopped it, you looked at it, you have your answer. Let's take a look. So it says the blue quadrilateral is the dilation of the red. So the red is the pre-image and the blue is the image. So that would mean, as you're just looking at it from observation, it's getting smaller because the red one is where you started and the blue is where you ended. And then what's the formula? So, let's before we do that, the center, where's the center? Well, from observation, it appears that everything seems to be growing from this 0 point right here in the center. 0 seems to be the center. Because if I look from 0 to k prime and 0 to k, I see that k prime is 3 and k is 6. So I can see there that, yes, this is, looks like probably the center because now I have that's half, right? And if I look at 0 to j and j prime, I can see that j prime is 1 and j is 2. So it seems to be a half, and I think the number is going to be a half. But the center is certainly here at 0. The 0, by the way, the center could be anywhere. It could be outside. It could be literally the 0 could be right here. You could enlarge or shrink everything from this point. What would happen then is the whole item would move away. Right now it's getting larger and smaller, but if your point is outside of the figure, it's going to move away from you or come closer to you, depending if you're enlarging or reducing. But what was the formula? The formula for the for the for the scale factor here is that we take the ending length of any one of these rays, if we will, and divide it by the starting length. That's what it showed in words. It showed that in that previous slide. So what is the ending length? Let's take 0 to k prime, which is the ending length of the on this x 0 to x, right? That ray there, or 0k, that ray. So given that, we're going to say that the ending length is, so the scale factor, the factor is equal to 3 divided by the starting length, which was 6. And that equals 1/2. And you can see that that's everywhere. That's exactly what it is. From j and j prime is a half, right? So I think we're in pretty good shape. Um, so that's the answer here. We have a center of 0, our c is at 0, and the scale factor is 1/2. Okay, here's a real world problem we're going to look at. Example 2. So it's a scale model. We're talking about little cars and trains and planes, little models at this point. It says the packaging list a model car's length as 7.6 centimeters. That's the length of the model car in this package that got listed on the box or wherever it was listed. It also has the scale factor of 1 to 63. What is the length of the actual car? Well, the way we would solve that is we say to enlarge the model car, because it's a little model car, they want to know the actual size, so we're going to be enlarging it. You can just by words, we're going to enlarge it. To enlarge the model car to the actual size, you use the scale factor of 63. Here's our 63 scale factor right here, 1 to 63. So what does that mean? That means 1 centimeter to start with is going to be 63 centimeters when you're done. So to enlarge the model car, use the actual size, use the scale factor 63. You multiply 7.6 centimeters by 63 to get 478.8 centimeters, or about 4.8 meters for the length of the actual car. So you multiplied the model or the full size car. You could have gone in reverse. They could have said that the car is 4.8 meters long. We want you to cut this down to a scale factor of 63. Well, then you would have ended up doing that division, and you would have gotten 7.6, okay, centimeters. Okay, example 2, check your understanding. It's your turn. The height of a tractor trailer truck is 4.2 meters. The scale factor for a model of the truck is 1 in 54, 1/54th. Find the height of the model to the nearest centimeter. Okay, you give it a try, and when you're finished, we'll at least talk about it. Okay, so what did you come up with? The answer to this is about 8 centimeters. And what did you do to come up with that? You took 4.2 meters, so 4.2 meters converts to how many centimeters? So you divide by or multiply by 100 centimeters, right? So it's going to be 420 centimeters. And then what are we going to do? We're going to multiply that by 1/54th, or divide by 54. So we divide by 420 by 54 as the scale factor, and we're going to end up with 8 centimeters. Everybody see that? I hope so. Objective 1C. So this is the third slide in our Objective 1 slides. Locating dilation images. Suppose a dilation is centered at the origin. Right here, we've talked about origin-centered dilations in the past. Here's one right there at 0, and on the right side, it's up there at 0. Okay? It says you can find the dilation image of a point by multiplying its coordinates by the scale factor. So what is that saying? So in the first one, the scale factor is 4, and we're saying that x comma y yields 4x comma 4y. The scale factor is 4. So what does that mean? We look down here, we see that A, in the beginning, here's our pre-image, 0 to A, and it's 2 comma 1, where A ended up. So if we multiply, if we're now we want to find the image, we're going to multiply the pre-image by 4, and we're going to come right up here to 8 comma 4. When what is that? That's 2 times 4 is 8. 1 times 4 is 4. And we're along that ray. The slope of the line does not change. We stay on, according to the previous slides, we stay on that ray. We never leave the ray. Okay. All points A on this ray from 0 to A lie on the ray. Scale factor 1/3. X comma y yields 1/3 x comma 1/3 y. Well, we can see that here. We go all the way down to, let's say we started at down here at B, which is 9 comma minus 6, or -6 right down here. And we're going to end up by going 1/3 of that. We take the x value 9 divided by 3 and end up at 3. Here's x equal 3 right here. And we divide y by 3. Y is -6. We end up with -2. Here's -2 right here. So here's our new b prime, which is 3 comma -2. We've now reduced it in length, staying along the ray. We don't slide off the ray, we stay on the ray. Okay, example 3, using scalar multiplication. To dilate a triangle from the origin, find the dilation images of the vertices. Enter all 6 vertex coordinates in a matrix, and then multiply each matrix entry by the scale factor. Multiplying a matrix by a scalar in this way is called scalar multiplication. So we're going to look at triangle PZG. Has vertices at P 2 comma 0, x is 2, y is 0. Z, x is -1, y is 1/2. G, x is 1, y is -2. Use scalar multiplication to find the image of triangle PZG for a dilation with the center at 0 and a scale factor of 3. And then it's asking you, it says draw the enlargement. Well, we're going to do that. It's already done here, but let's talk about it. So we're going to fill in a matrix. It says fill in a matrix with the coordinates of the points. So I've drawn a 3 by 2 matrix. Here we see this says x coordinate on the top row, and the bottom row is the y coordinate. And the vertex P, Z, and G are listed across the top. So if I'm going to say that I'm going to enter in for the angle P, x of 2 and y of 0, you see I put the 2 in the x coordinate column and the 0 in the y coordinate column. And then I'm going to do the same thing for Z, which it says -1 and 1/2. And G is 1 and -2. And that's the matrix for triangle PZG. If you want to see, then we'll just pick one. Let's pick P. P is way over here, right? Here's P. Okay. And it says 2, 0. Well, in the X value, it's out 2, 0, 1, 2. And in the y-axis, it's not anything. It's 0 on the y-axis. Okay. So that's how you see the 2, 0. We know all about that. So that's the point. So for Z, it's -1 and 1/2. That's over here. -1, 1/2 is right here. Okay. And 1 and -2 for G is X is 1, G is -2. We're down here. So now they say, in the next step, they're saying multiply this matrix that we just filled out, the PZG matrix, multiplied by 3. Here's the 3 we're multiplying, the PZG matrix. And to do that, scalar multiplication, you just take that 3 and multiply it by each term in the matrix. And when you're multiplying it, you're now filling in a new matrix on the other side of the equal sign with the values. So 3 times 2 is 6. 3 times -1 is -3. 3 times 1 is 3. And then when you do the y values, it's 3 times 0 is 0. 3 times 1/2 is 3.5. Or, excuse me, 3/2. And 3 times -2 is -6. Now we've multiplied. Now all you have to do is pick those points, your new P, Z, and G, which are P prime, Z prime, and G prime, and place them on the graph. So for P prime, we're going to have 6 and 0. So P prime is started over here at P. Now we're going to P prime. This is 1, 2, 3, 4, 5, 6. So we had 2 and X. We multiplied by 3 and got the 6. Here's the 6. And Y is 0. So we have no vertical motion right here. Okay. And then when we do Z, it's -3 and 3/2. So Z is over here. We go -3, 1, 2, 3. Here's -3. And 1, 3/2 is right here, right in the middle between 1 and 2. And then finally, 3 and -6 for G prime. G prime is 3. So for X, 1, 2, 3, and down -6. 1, 2, 3, 4, 5, 6. So now that's how we've enlarged this from 0 as our center point. Everything is enlarging from there. Okay, do we see that? So the vertices of enlargement are P 6, 0, Z -3, 3/2, and then for G it's 3, -6. Okay, example 3, check your understanding. Uh, Again with triangle PZG. It has vertices at P 2, 0, Z -1, 1/2, and G 1, -2. Use scalar multiplication to find the image of PZG for a dilation with center at 0. This is just like we just previously did. 0 is the dilation point, center, and scale factor of 1/2. So now they're saying draw the reduction. So we're going to be smaller than, the triangle is going to be smaller than this one. So why don't you go ahead and try it? I'll give you some time. I know you have to draw up your graph and everything. And I'll wait for you. Okay, now I'm sure you've taken all the time you needed to draw this up and see what you come up with. I've got a graph paper on the screen here and I've marked it off and we'll talk about how I marked it. And I have the formulas out, just like we did before, the matrices, And I'll have the scale factor. So the scale factor is 1/2. The matrix C, the matrix that we're multiplying is the same one as before. 2, 0, -1.5, 1 and -2 for P, Z, and G. And now we're just going to do the multiplication on the PZG matrix times 1/2, and we're going to get our new values, and we're going to plot them. So the first thing we're going to do is plot the original triangle. And the original triangle I'm going to plot in red, and it says 2, P is 2 and 0. So 2, oh, and by the way, these are quarters. Each line is a quarter. The major lines here would be 1 and 2. So this is 2 out here, and this is 1, and this is -1, and -2. This is 1 and 2, and this is -1 and -2. Okay? So now it says we're starting with P of 2 and 0. So here's P of X is 2, Y is 0 is right here. This is P. Okay? Now Z is -1 on X and 1/2. So -1 is right here and 1/2 is right here. You see why I drew them big. Now these are Z, and G is 1, X, and -2 in Y. So 1 in X and -2 right here. So this is ZG. Okay, those are our points. We can draw the triangle. I don't think it's as necessary, but let's see. Kind of. What do you think? That one. And I wish I had drawing tools for this. Well, not too bad. I've done maybe better, but not too often. So there's our triangle. That's the original triangle. If you look at it, it's just very big because of the scale factor on the chart. Anyway, so now we've multiplied it. And what did we get? We took 1/2 times 2, and we got 1. Here's our 1. I'm going to do this now. I'm going to do these in blue. So now we took 1/2 times 2, and we have 1 right here. And 1/2 times 0, we have 0. So P prime, I'm going to put primes on these. All right. So P prime is over here, and it's now 1 and 0. So it was 2 and 0, now it's 1 and 0. So it's right here. This is P prime. And then we get the next one, which is Z, which is Z prime, which is -1/2 and 1/4. So -1/2 is right here, and 1/4 is right here. So this, what did I say it is? This is Z prime, Z prime, Z prime. Okay, and the last one, G prime, is 1/2 X and -1. So 1/2 X is right here, -1 is right here. So here is our new G prime. If I draw this triangle, I'll try it as best I can. There, and here, and there. So you can see it's about 1/2 the size. Hopefully that makes sense. So the vertices of our, oh, it says enlargement there. We're going to fix that. The vertices of our reduction are P equals 1 comma 0, Z equals 1/2, -1/2, 1/4, and G is 1/2, -1. Okay, thank you.